Okay, let's dive right into this. Today, we're taking a pretty fascinating journey into the very structural heart of the materials that literally build our modern world. We're looking at Chapter 6, Mechanical Properties of Metals. But, rather than just running through a dry list of textbook equations, we're going to look at this as a narrative, specifically the life cycle of a load. So, what exactly happens both at a microscopic atomic level and a macroscopic level when a metal is subjected to immense mechanical forces? Let's find out.
Here's our roadmap for this explainer. We'll be hitting 6 main stops. First, forces, stress, and strain. Second, elasticity and Hooke's law. Third, plasticity, the permanent shift. Fourth, yield and tensile strength. Fifth, ductility and toughness. And we'll wrap up with resilience and hardness.
Starting things off with Section 1, Forces, specifically looking at stress and strain.
To start right at stage 1 and really ground this physics in reality, picture this. You're dangling high up in the air on a ski lift. The structure holding you up is experiencing some massive mechanical forces, because obviously before a material can bend or break, it has to actually be subjected to a force. The cable itself is under simple tension, a pulling force that's trying to stretch it out. Meanwhile, the drive shaft operating the whole lift is experiencing torsion, which is more of a twisting, shear force. Our structural integrity and, honestly, our lives depend on engineers knowing exactly how these materials are going to respond to these specific loads.
To predict that response, engineers use a concept called stress, represented by the Greek letter sigma. But stress isn't just the raw force. It's the magnitude of the applied force, F, divided by the original cross-sectional area, A0, of the material before any load was applied. Now, why do we normalize it against the area? Well, because it gives engineers a universal standard. Think about it. 10,000 pounds of force on a tiny thin wire, absolute catastrophe. But that same force on a massive solid steel beam, barely a tickle. Normalizing the force allows us to compare completely different materials regardless of their physical size. Now, what's really fascinating here is how we pair the concept of stress directly with strain. On the left is our visual model for engineering stress, force pulling on a specific area. On the right, we have engineering strain. Strain is basically the physical consequence of stress. It represents the actual degree of deformation relative to the material's original dimensions. So, for tensile strain, it's just the change in length divided by the original length. And since you're dividing length by length, strain is actually a dimensionless parameter. It just tells us proportionally how much the material has stretched.
Moving right along to Section 2, Elasticity and Hooke's law.
All right, so we've applied a load, but initially we're still in a safe zone. In this phase, a material can bend, but it bounces completely back to its original shape. Why does it do that? Well, under a relatively small load, the bonds between the metal atoms simply stretch. They basically act like tiny, incredibly stiff springs. When you unload the force, those bonds just spring right back to their initial unstretched positions. Because of this, elastic deformation is entirely non-permanent. It is 100% reversible.
But, as you might guess, not all atomic springs are created equal. This curve shows the interatomic force versus the separation distance between atoms. And this brilliantly illustrates why some materials are incredibly stiff and others just aren't. A material's stiffness, which we call its elastic modulus, or Young's modulus, is directly proportional to the slope of this curve right at the equilibrium resting point. The steeper that slope, like you see with the red line, the more strongly bonded those atoms are. And that translates directly to a larger elastic modulus and a much stiffer material that heavily resists stretching.
Which brings us to Section 3, Plasticity, the permanent shift. So, let's see how this builds into our next critical phase. What happens when we push those little atomic springs just a bit too far? We escalate the force and we cross over into plasticity. There is a massive, fundamental divide between these two states. Elastic deformation, as we established, is totally reversible. It relies on mere bond stretching, and on a graph, it represents a clean, linear relationship between stress and strain. But plastic deformation, that is permanent. It involves actual atomic displacement, and mathematically, the relationship between stress and strain becomes highly nonlinear. You fundamentally altered the material at this point. Visually, at the atomic level, the change is pretty stark. Applying a heavy load doesn't just stretch the bonds anymore. It literally forces whole planes of atoms to slide past one another. When the load is removed, when you let go, the elastic stretch recovers, sure, but those sliding atoms, they actually remain displaced in their new positions. The structural integrity has changed forever. This deformation is entirely non-recoverable.
And we can trace this physical reality right on a stress-strain curve. You start down at the bottom left, moving straight up that linear elastic deformation line. But eventually, the curve yields. It bends over into a nonlinear path. If you were to release the stress while you're up in that curved upper region, the material unloads parallel to the elastic line. But notice it doesn't return to zero on the strain axis. That gap sitting at the bottom, that is your permanent plastic strain.
Next up, Section 4, Yield and Tensile Strength.
Since we know materials permanently deform, engineers absolutely need exact numbers to prevent a catastrophe. The first major threshold here is the yield strength. Because the transition from elastic to plastic is usually this gradual, sweeping curve rather than a sharp, obvious corner, engineers need an agreed-upon standard for when a material has officially deformed. So, yield strength is defined as the precise stress level at which noticeable plastic deformation has occurred. It's typically measured by drawing a parallel line at a standard offset of exactly 0.002 strain. If your building hits this stress level, its beams are permanently bent. Simple as that.
But what if you just keep pulling past that yield point? Well, the stress required to continue stretching the material actually goes up until it reaches the absolute peak of the engineering stress strain curve. That peak right there is the tensile strength, the absolute maximum stress point. For metals, hitting this point means the material begins a rather terrifying process called necking. The cross-sectional area in one localized spot rapidly shrinks, literally looking like a neck forming. This acts as a fatal stress concentrator, rapidly plunging the material downward toward an absolute fracture.
All right, Section 5, Ductility and Toughness. As we're pulling a material all the way to failure, we also really care about how much warning we're going to get before it snaps. Ductility is essentially a measure of the total amount of plastic deformation a material undergoes right before it finally breaks. A highly ductile material is going to stretch out significantly, giving us plenty of visible warning that something's wrong. Whereas a brittle material, it's just going to suddenly snap without warning. We quantify this using percent elongation, how much longer the material got relative to its original length, or percent reduction in area, which measures how much that necking process shrank the cross-section. Toughness, on the other hand, is the total amount of energy a material absorbs before it fractures. Graphically, it's approximated as the entire area under the stress-strain curve. Look at this comparison here. It's super revealing. Ceramics, in blue, go super high on the stress axis, but they fracture almost instantly, so they are incredibly strong but brittle, meaning very small toughness. Unreinforced polymers, in pink, will stretch practically forever, but they can't take much actual load, so again, small toughness. But metals, in green, they exist in this amazing Goldilocks zone with an incredible balance of both high strength and high ductility, resulting in massive toughness. They can absorb a huge amount of energy before breaking. And finally, Section 6, Resilience and Hardness. To wrap up our analysis of mechanical properties, we're looking at a material's capacity for energy storage and its resistance at the surface layer. While toughness is the total energy up to breaking, resilience is kind of like its more cautious cousin. It's a material's specific ability to absorb energy strictly during the safe, elastic deformation phase and then release it upon unloading. Think of a perfectly tuned suspension spring on a car. Mathematically, it's specified by the modulus of resilience, represented purely by the area under the linear, elastic portion of the curve, right up to the point of yielding.
Then we have hardness. While pretty much everything else we've discussed today involves pulling a material apart, hardness evaluates a material's localized resistance to surface deformation, like scratching or denting from compressive stresses. It's absolutely critical for any material subjected to daily wear and tear. Engineers don't generally use stress-strain curves for this. Instead, they rely on specialized physical tests that literally press a tiny indenter into the surface, using standard measurement systems like the Rockwell and Burnell hardness scales.
So consolidating this entire life cycle of a load, we can look at this summary metrics. Stiffness prevents that initial elastic bending. Strength resists permanent plastic deformation. Ductility dictates how far it'll stretch before catastrophic failure, and hardness keeps the surface safe from localized compressive damage. Every single one of these mechanical parameters interlocks to help engineers safely design the machines, buildings, and infrastructure that we rely on every single day.
And that leaves us with a final thought to end on. We've walked through the literal life cycle of a load today. So, imagine you're sitting at the drafting table. You are engineering the tracks and the chassis for the next generation of ultra-high-speed rail. Which specific phase of this mechanical life cycle are you going to prioritize? Do you maximize stiffness to prevent any swaying high speeds, or maybe you push for toughness to ensure the metal can absorb the impact of an unexpected anomaly without completely shattering? It's balancing these exact properties that makes modern engineering such a profound science. Thanks for hanging out and learning with us today.